This is Team 58's Design Challenge 1 presentation. Our client was Team 57, and our objective was to make a robot that drives in a circle of a specified radius. For our design specifications, the first one was that the robot will drive in a circle of specified radius n times. The robot was not necessarily a full-scale robot and had to contain wheels. Both the radius of the circle and the amount of times the robot traverses the circle are input by the user, and it must stop once the trip is completed. The constraints were that the robot should not exceed 1 foot by 1 foot and should aim to be at least 5 inches by 5 inches. The questions we asked our client team were what was the maximum minimum radii that we need to accommodate for? And their answer was that the minimum radius could be whatever we wanted depending on the size of the machine we built and whatever that allowed. There's not much need for a maximum, but we could also define it if we wanted to.
For the technical specifications, our first requirement was to complete a perfect circle, and the technical need for that was to complete a radius in centimeters, and we decided that the requirement had to be within 0.5 centimeters plus or minus, and we targeted to be within 0.25 centimeters. And our second requirement is that we need to complete a certain number of trips, and that was the number of 360-degree turns, and we required that it should be within plus or minus 10 degrees, and we targeted to be within plus or minus 5 degrees. And our final requirement is that it should be relatively small to fulfill a certain dimension requirement. And the requirement was 12 by 12, and we targeted to be within 5 inches by 5 inches. For the system diagram, we have a radius input and the number of circles, which is input by the user into the console, which is processed by the Raspberry Pi to compute the current speed for the wheels, which is output, and then a specific output is put to the motors, and the electricity feeds into the battery, which feeds into the Raspberry Pi.
For alternative options, we considered a 4-wheel drive using tank treads, a 3-wheel design, or simply using the IMU in our design. The 4-wheel drive we decided to not go with because the tank tracks, it would have messed up the math that we did to program the robot. The tri-wheel design we couldn't go with because the rear wheel was not able to be attached well enough to support the weight of the battery on the back. And the IMU we did not go with because the code would have been too complex to calculate within the time that we had to build the robot. Construction, we started by creating a chassis with 2 front wheels in the front and a ski in the back. The Raspberry Pi mount was attached on top of the chassis, hanging out over the motors in the front, like in the picture in the bottom left, much like a shopping cart. The battery mount was constructed over the ski in the back, like a pickup truck bed, as you can also see in the bottom left side view picture. During operation, the motors were run at different speeds, resulting in the tail of the vehicle sliding along on the ski. It's like a whiplash effect.
The program accepts inputs for the required radius of the circle to be driven and the number of circles for the robot to drive. Using a constant base speed for the outer wheel and a pre-measured distance between the center of both wheels, the program calculates the ratio between the outer and inner wheel speeds to determine the speed in degrees per second of the inner wheel. A while loop is used to determine the number of circles driven. The time driven for each circle is determined by finding the radius of the circle that the inner wheel travels along. This is then used to calculate the number of degrees that the wheel must turn, which is then divided by the speed of the wheel to find time. After testing, it was found that while the robot completed the objective, it was not perfectly accurate in the radius of the circle driven, nor the number of rotations driven. However, these inaccuracies were in a reasonable margin of error. The robot was off in the number of rotations by about plus or minus 0.2 rotations and was about plus or minus 0.3 centimeters off the desired radius. The robot would often travel for slightly too short each rotation, thus the code accounted for this by adding time driven at the end of each driven circle. All in all, we were satisfied with the results considering the time constraint of the challenge. With more time and testing, these errors could be largely solved and a better product could be developed. As shown, the robot clearly fits between the 1 foot by 1 foot size requirements given by the client.